This video tells you about the ratio test, which is a test for series convergence. So it answers the question, when does a series converge? And the ratio test provides an answer. It says if the limit as n goes to infinity, the ratio of consecutive terms exists is equal to L, and L is less than 1, it converges. If L is greater than 1, it diverges. And if L is equal to 1, no info. You'll have to try another test if L is equal to 1. Okay, so let's show that this actually works. And the way it works is by comparison with the geometric series. So the proof is by comparing our series with a geometric series. And the geometric series is one of this form, and the thing that we know about it is it looks actually very similar. Geometric series converges if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than or equal to 1. And if you're interested in that, I have a separate video that shows you this very result. Okay, so we're going to compare our series with the geometric series, and in particular, how does that comparison go? Well, let's suppose that the limit of these consecutive ratios, or ratios of consecutive terms, exists. Okay. Because you'll notice that's part of the hypothesis. If this limit exists, then we can tell you something. If that limit doesn't exist, the ratio test tells you nothing. So let's suppose that that limit exists. So we can use the ratio test. If L is less than 1, compare an plus 1 over an with an r that's going to be less than 1. But this does not actually always work. There may be no real comparison. However, now since the limit exists, for sufficiently large n, this ratio here, well, it's equal to L, right? Well, the limit is anyhow. What that means is that for sufficiently large n, this guy is actually going to be less than, not quite 1, but even actually a little less than 1, like 1 minus epsilon, for some positive epsilon. Okay. This thing, the 1 minus epsilon, we're going to call that r. So what this means is there may be a bunch of terms where the ratio is all over the map. But eventually, when n is large enough, because the ratio of terms in absolute value is going to a limit L, and that limit L is less than 1, eventually you got to get within epsilon of L. So that's the point. That's the epsilon from the epsilon delta argument and definition of the limit. Okay, so that, now, given that, now what can we say? Well, this inequality tells us something. So given r is equal to 1 minus epsilon, well, we've got this ratio. It's less than r. And what else happens? Well, you know, that's the same thing. If I multiply both sides by an, I'll get an plus 1 is less than r times an. Well, gosh, that means that that's less than r squared an minus 1, and so on, up to r to the n plus 1 times a0. Well, not quite. Not quite. That a0 may be a problem. But at the very least, for sufficiently large n, and so it is worth noting that kind of without loss of generality, you don't really have to worry. Okay, so watch out for that sort of thing. If it were the case that we were dealing with this ratio being less than r for everything within fun, but for sufficiently large n, so that means we can't go all the way up to rn plus 1. But that's okay. The convergence of a series really only depends on the infinite terms that happen after some point. Okay, so without loss of generality, write our series as, here's the original series. Here's the first part. Here's the rest. And the point is, this part here has the ratio less than r, and here something else. The point being that something else doesn't matter for convergence. This can be ignored as far as convergence goes. This is the only part that the second term there is the only one that matters. Okay. Well, what does that mean? What that means that without loss of generality, we just assume an plus 1 over an is less than r. So an plus 1 in absolute value is less than r to the n plus 1 times a0. Okay. The reason being that we're essentially relabeling the capital N with 0. No harm done. And that's what we really wanted to have happen up here, but couldn't. But that's okay. All right. So given that, therefore, the sum of absolute values of an, n equals 0 to infinity, is going to be less than the sum absolute values r to the n. Oh. Well, that means that if geometric series converges, so does our series. And since r is equal to 1 minus epsilon for positive epsilon, this happens. Now, on the other hand, what if L is greater than 1? Then the same kind of argument applies. But let's say 1 plus epsilon is now less than the ratio for sufficiently large n. As you might expect, we're going to set this 1 plus epsilon equal to r. So what does that mean? That means that in that case, our geometric series is less than our actual series. Therefore, since geometric series diverges, so does our series. And that's the end of the argument. End of proof. One little comment. The ratio test only cares about magnitudes or absolute values. Therefore, it implies absolute convergence or divergence.